You guys online hear me okay? All right, and the people online, can you guys hear me okay?
Yeah.
Thanks. Well, good morning. Good morning, everyone. I am today we're gonna talk about what if we want to increase the fidelity of these calculations. What if we want to get more resolution? When we hopefully you guys could see from yesterday that if we want to increase the resolution, it's not a simple, well, make it 2 times bigger or 4 times bigger. In subchannel, when we went from an assembly averaged flow where we had a 20 centimeter size flow mesh cell to a single channel where we now had a centimeter size channel, that's a factor of 20 in X, factor of 20 in Y. And if you're going to shrink it down in X and Y, you also want to shrink it in Z. So it's a factor of 20 smaller in Z. And so just the sub-channel, to go from an assembly average flow to modeling every channel, you're going a factor of 20 cubed bigger in size. So you're going a factor of 8,000 bigger. So if that problem took 1 minute on your one processor computer, going for a assembly size mesh, it will now take 8,000 minutes in general. And so just a simple jump, not even getting to CFD, but just big subchannels to small subchannels increases orders of magnitude the size of the problem. The same can be said for fuel. What if we wanted to model every fuel rod in the core instead of modeling one in every assembly? Well, there were 17 by 17 fuel rods in the core. So we just jumped up the number of fuel rods by a factor of several hundred. In radiation transport, we're in a similar boat. If we want to have more fidelity, we can't just say, let's increase this by a factor of 2 or 4 or 5. We have to make a orders of magnitude jump in the size of the problem. So a project that I worked on while I was at Oak Ridge National Lab was called CASTLE, and the Consortium for Advanced Simulation of Light Water Reactors. And so I'm going to talk to you guys about some of the things that we did in that project and the code we worked on. So originally, on the first day of class, I talked about design engineering, and when you're doing an original reactor design, you have to establish the design, you have to do safety analysis and optimization, you have to understand how it impacts radiation shielding and consequences and deal with uncertainties. And every time you reload the core, you have to do many of those same things. For light water reactors, all those things can be done with the tools that we talked about yesterday, with the methods, with the multiphysics coupling, all of that can be done. So it's always important to keep your eye on what is the driving purpose for what you're doing, what you're coupling, and why are you coupling. So the CASTLE project was started in 2009. They put out a call for proposals for a 10-year focused research and development effort to look after what are some of the most significant challenging problems for the existing light water reactor industry. What are those things that are holding them back, that are preventing them from being economical? And what of those things, which of those things could be addressed with advanced computing and simulation? And so we identified in that project a suite of challenge problems. So the first challenge problem was we wanted to understand how that fuel and that cladding interact, because when that fuel is expanding and swelling. It is increasing its diameter. And as the cladding is creeping down on the fuel, it's shrinking that gap. And when they start to come into interaction, that's when you can have fuel failures. And so in general, the way that the industry says, I don't want to have fuel failures is if I start getting fuel failures by ramping up in power very quickly, then I need to ramp more slowly in power. And if you're turning on the reactor once every year and a half, that's not really a big problem, because if it takes you 2 days to get up to full power instead of 1 day or instead of 30 minutes, well, you lost, a day of operation out of, a year and a half. That's not that big of a deal. But as people are starting to want to drive these reactors to be able to account for the fact that the electricity market has renewable energy feeding into it, and the amount of electricity fed in from wind and solar is varying, the utilities now are wanting to start adjusting how much energy they're producing with their nuclear reactors, because when the sun is shining and the wind is blowing, they don't really need more electricity. And so continuing to run the reactor at full power is just wasting its energy. It would make more sense to drop it down to a lower power and operate at maybe 20% power for a while. And then when it gets cloudy, then they can ramp back up to full power. But now they're changing the power up and down during the cycle many times, potentially. There are a few utilities in the US that are doing this right now. And at times they are doing it in a way that we go down to 20% power and stay for 2 weeks and then come back up. And at times we're going within the day. We may go from 100 to 80% to 100 to 60 back to 100, just changing it over throughout the day, trying to figure out how can they operate. But when they're doing that, fundamentally, they need to be able to go as quickly up and down as they can. Otherwise, they are wasting a whole lot of electricity that they could be generating and producing for the market. So cladding integrity during a reactivity insertion accident. So in a accident scenario, one of the, there are a variety of accidents that could lead to a reactivity insertion. One of the most common ones is a control rod ejection. And so in every US safety analysis, you have to identify what would be the impact if you were operating and you had a control rod that was partially in while you were operating. And then that control rod, a weld failed on the housing up above it, and that control rod shot out of the reactor. So when you lose that absorber, suddenly you're adding reactivity into the system, and you're getting a huge power spike right there where that control rod was. So there is a big concern with this type of accident of, is that cladding going to fail? Are we going to start melting those fuel rods that are right next to that? This is the kind of accident that we study. So PCI right now we study by doing the full core analysis and then identify which are the assemblies that are the hottest, which are the pins in that assembly that are hottest, and we pick out a few pins and say, let me evaluate whether that pin is going to fail by using a full 3-dimensional or 2-dimensional fuel performance code. We don't look at every single fuel rod because there are so many in the core. With a cladding reactivity insertion accident, you generally say, okay, well, I'm going to assume that the most likely to fail rod is the one sitting next to the control rod where it was. And so I'm going to assume that that's going to be the worst rod, and I'm going to focus on that one and make sure that one doesn't fail. But there are a lot of other fuel rods in the system, and it might have been a control rod that shot out of something where the fuel next to it wasn't going to be the one. So by only looking at a limited set, you're not sure where what is really going to happen in that type of an accident, which is the pin that is the most dangerous. The departure from nucleate boiling and flow regimes. This is a completely separate part, so I'm not going to get into that a whole lot. But just understanding how when you have subcooled nucleate boiling and then you go into full boil, how it transitions to a film of vapor next to the fuel. If you get into a flow regime where you lose that nucleate boiling and it has a film of vapor, the temperature in the fuel increases a whole lot. So this one was mostly a separated, isolated one. Up here, crud, I'll talk about in some more detail. I mentioned it before. You have metal ions that are flowing throughout a LWR that are picked up from corrosion of various pieces in the system. Corrosion mostly of the steam generator. And so those little metal ions, where there is subcooled nuclear boiling on the surface of the fuel rod, those metal ions will get deposited. And that deposit, that growth is called crud. And that crud can have boron inside of it, and boron's a big neutron absorber. So then during a loss of coolant accident, understanding what's happening in that full loss of coolant accident, understanding in much more detail what's happening. So as all of the safety analysis that's done for both of these situations have lots of safety factors built on, which really prevent the reactors from operating at what might be a higher power and more electricity if they could operate at that higher power. So really understanding what's happening in a loss of coolant accident surrounding those fuel pins and surrounding those water channels. And then grid to rod threading. So in the fuel rods are sitting inside of these assemblies, and they have the little springs holding them in place. They're not welded anywhere at all. And you have really fast water flowing vertically through this system. And so if you have a skinny pencil-sized, 3-meter tall pencil-sized rod and water flowing past it, that rod is going to vibrate some. And as it's vibrating against that rod, that grid spacer, it can start to wear a hole in the fuel rod. It can start to and lead to a possibility of fuel failure because of that. So on one hand, that's do we understand how the cladding wears against it? Do we understand the forces from flow-induced vibration? But it also has a full global connection to the rest of the environment, because how much that cladding changes shape is going to impact how much that spring is able to keep a pressure on it. Because most of the time, that wear happens when there's separation. So if the original pin were sitting in the grid spacer and had some springs here that were helping it lock in place, if this cladding shrinks, then you get a gap around those springs. And now that pin can vibrate back and forth and start hitting those springs and wear a hole in it. And so understanding the global effect on how that dimension changes in the fuel comes into play. And so all of these key challenges are requiring some understanding at the core, but it's requiring it at a much higher resolution than the traditional codes have provided. So in the traditional codes, you might get, here is my assembly power. And if you wanted to get the actual pin power, then you kind of had to do a hokey thing where you say, here's the shape of the power and the lattice physics calculation. And here's the global power, and we're just going to assume they overlay. And there could be a lot of error in that. But with this, if we had the ability to know every individual fuel rod's individual power, temperature, coolant state around it, then we could have much, much greater detail, and we could start to look at how does every individual fuel pin behave. How is this crud building up on the surface of all these fuel rods? How do their individual temperatures and the coolant flow around these things impact that? And so it really requires a higher level of fidelity. So one of the key pieces of this was we need a higher resolution fundamental core analysis code. But I'll point out, the idea for this is not necessarily to do any design engineering. So the goal isn't just we want a more resolution so we can do more design or higher resolution design. We can do for LWRs all that design work we needed. These things are costing money. And because they're costing money, if we can eliminate them, then we can suddenly be able to save a whole lot more money and operate at a higher powers, and still know that we are operating in a safe state because we've gotten more insight and understanding into what's happening. So to do this, it's not something that can be done by one person. This was a group of 10 institutions as a core group. Oak Ridge was the lead, with the Idaho and Los Alamos and Sandia National Laboratories all working with us. We had 3 universities closely working, Michigan, NC State, and MIT. And we had 3 private companies. Westinghouse makes fuel and makes reactors. TVA operates reactors, and EPRI does general nuclear analysis and support for the nuclear industry. So researching many of these same problems with the sort of traditional tools. So to do this, we wound up with a sort of guiding philosophy in how do we want to handle these codes to do this multiphysics problem. So we wanted to raise the level of accuracy of the thermal hydraulics, of the fuels, of the neutronics, incorporate some chemistry. And so everything we needed to raise to a higher level of resolution. And there are a lot of people with a lot of opinions on a lot of ways to do this. For us, our guiding philosophies were we wanted to make sure that each of the physics solvers is strong on its own. If we have a neutronics capability, we want it to be a really good neutronics capability. With thermal hydraulics, we want it to be really good thermal hydraulics. So every one of those codes, we said, you have to have validation. You have to run your code. You have to prove that it's right. You have to compare it with experiments. You have to understand what error your code has. So when you say, hey, this is my temperature, you aren't just saying this is my temperature. You're saying, I know my temperature is within plus or minus 10 degrees because I've modeled so many different problems that I'm not going to tell you the temperature. I'm going to say this is the temperature and this is how accurate it is. It also allowed every development team to use the best methods that are available to them. If we tried to say, let's choose one system that works for everyone, then you are very likely to end up with some decisions that are difficult for one team, that one team says, this isn't the best way to do this. And so we said, let's let every development team choose whatever methods they want to work the best for that individual code, because we want that code to be as good as it can be. Because the level of fidelity was going to have to be raised, we said every code has to be parallel. We have to run with thousands of processors in parallel. You need to be able to use, you can if you want, and probably should, leverage a whole lot of the parallel computing tools that are out there. And one of the parallel computing tools that is very common and available is math solvers. So if you have a matrix and you say, this is my matrix, like we were drawing some problems the other day, if you say, I have a matrix and it's distributed in parallel and I want to solve this problem, there are math solvers that you can just say, here, you do this, you take care of that. And so as much as possible, most of these codes aren't going to want to have a bunch of nuclear engineers writing a bunch of advanced math codes. It's a whole lot easier to say, let's let the mathematicians do what they do well and work with them. And then we had to have an overarching team that was working with all of the codes to try to get all of these things integrated and working happily together. And so in that, we had to be flexible in the physics coupling. We needed to make sure we were transferring all data in memory. When you're using a computer that has thousands of processors, one of the slowest things on that type of computer is writing data to files. They're very good at passing memory between processors, but they're really very slow at saying, okay, now let me go to the system and write my data to the system. We have to be very careful about consistency across physics. And so if I'm in the neutronics code and I want to pass a power to a fuel or a thermal hydraulics code, am I passing the power density, the linear power, and what geometry was I passing it on? So I was passing it every fuel pin at a time, or maybe I'm doing radial rings within a fuel pin. How am I making sure that when I pass you this power and you get the power, it's consistent, that you got the power that I wanted you to get and you used it in the way that was intended? And so there have to be a whole lot of checks and balances to make sure, if I give you this much power, why don't you tell me the total power I gave you? Just so that we can be sure that if I thought I gave you 1,000 megawatts, then you should think you got 1,000 megawatts. We should have checks in there to make sure of that. And so it has to be built into your processes. How do you make sure you're dealing with consistency in these communications? We also have things like there's geometry approximations. If you remember on the sub-channel, when we talked about the grid spacers, we didn't say anything about we're modeling flow through grid spacers. We had some model that accounted for how the flow got through the grid spacers. And so if you're not going to model the grid spacers in the thermal hydraulics, are you modeling that grid spacer in the neutronics or not? Because if you model it in neutronics, you could say, here is the heat that is generated inside of that grid spacer, because that grid spacer is metal and there will be neutrons absorbed there. So it will be directly heated. Or maybe the neutronics is going to say, I don't need all of the detail of the grid spacer either. So I'll just add a mixed fuel water combination in that grid spacer. And so understanding the consistency amongst all of these different approximations that they have. We needed to make sure we had research efforts going into how do we couple codes? How do we have a driver code? Which of these codes is in charge, or do we have another code that's in charge? And then if every one of these codes is parallel, you have a global parallel problem. One code says, I need 100 processors, and another one says, I need 1,000. Well, what do? How are you going to do that? Are you going to use 1,100 processors? What process do you want to have? And then the driving aspect of always focus on the challenge problems and the end users. Because many research projects end up with really interesting things that the researcher understood and nobody else was able to pick up and use or do on their own. So we wanted to make sure we weren't writing this capability for us to do cool, interesting science. We wanted to be able to get it to somebody in industry so that they could pick it up and use it and say, let me understand my reactor so that I can figure out how we save money. And so what are those challenge problems? What does it need from our system? What are the users that are going to be modeling these challenge problems? How do they need to interact with things? Any questions? Okay, so if this was our traditional multi-scale approach for heat generation, where we have one direction, thin cell, lattice, down to core, we had to assume some states, we had some approximate boundary conditions, we made some smearing of materials to make more average smeared materials here, we approximated temperatures and densities, we approximated boundary conditions, we fed it down here, and this was where our core was coupled with all of our other physics. We tabulated a whole bunch of things here so that in advance we had to pre-process everything. But we didn't have individual fuel temperatures. We didn't have the coolant density in each one of these channels individually. We had, here is this whole assembly average temperatures. Here's the whole assembly average densities. So a example of increasing that level of fidelity is we put together the impact code. So with this code, what it said is, let's remove the pin and lattice, but we couldn't jump all the way to that full 3D transport with hundreds of thousands of energy groups. That jump wasn't a factor of 1,000 or 1,000,000 more. That was factors of at least 6 orders of magnitude higher. So we said, what we can do is get away from the individual single assembly, and we can do the full 2-dimensional slice of the reactor. And that way, there isn't any what is happening at these interfaces of these assemblies that have arbitrarily defined boundary and neutrons don't see. And so it's doing with that high fidelity and energy. We didn't go all the way up to the 10 to the 5, but we got in that upper end. So thousands of energy groups doing very complete resolved geometry and materials. And it is able to get, if this is going to interact in a coupled physics environment, it's going to be able to get the specific state from the other physics. So it's able to get every individual fuel rod has its own temperature at each axial plane. And this is done for 50 axial planes. And so we do the same two-dimensional transport calculation at 50 different axial heights. Each has its own temperatures, each has its own densities. And by doing it in 2 dimensions, we need to account for the 3D effect. And so we know if you just have a 2-dimensional slice of a reactor, but there's some neutrons that leak out axially, some would leak into some planes and out of some planes. And so we have it coupled with a full 3-dimensional, what I'm calling in here diffusion. It's really spherical harmonics transport. And so this, we do a collapsing down in energy to 50 groups, and this is where we're doing our full expensive eigenvalue calculation. And so we are iterating back and forth because when we know our full 3-dimensional neutron fluxes, then that can lead to a source for each of those 2-dimensional slices. And we couple a whole lot of 2-dimensional slices with a full 3D transport solve, so that we can get a transport calculation that accounts for every individual fuel pin. So within the fuel pin, within each fuel pin, we're modeling explicitly the cladding and the gap, and we're putting radial burn up so that we can have different amounts of fission products in each of those radial regions. We have, usually we're using 50 axial mesh. And if we look at the mesh for even just a single pin cell, we wind up with our material definition is going to look like this. But then our mesh winds up looking like this. And so we have in the range of 100 mesh cells for every one of these fuel pins. And we have several hundred fuel pins inside of an assembly and several hundred assemblies and 50 axial regions. And we're doing each of those 50 axial regions with 1,000 groups. And so this problem all by itself, this code winds up saying, you may have been used to using core diffusion when you ran it on one processor and it finished in 5 minutes. But in order to do this calculation, I'm going to need 2,000 or 3,000 processors, and it's going to take me 30 or 45 minutes to get it done. But it can be solved if you have a computer that has thousands of processors. Then waiting instead of 5 minutes, waiting 45 minutes, 30 minutes, isn't that long. It's not that bad. You can say, yeah, I can wait for that. So the sort of infrastructure for doing all of this looks like this. That impact code is one of the neutronics capabilities. It's just the radiation transport. We have Origin does the isotopic depletion, and we also have a Monte Carlo code built into this. And so impact and shift, one is deterministic transport, one is Monte Carlo. The Monte Carlo code has no approximations in anything. There are no approximations in space, no approximation in the direction the neutrons travel, or no approximations in the energy distribution. But it has different capability that I'll talk about in a little bit. All of it is built on sort of the same fundamental data. And so there is the same data, no matter which code you're using, it all has the same data. For thermal hydraulics, the Cobra TF code is what we have. It is that sub-channel thermal hydraulics capability. It can be run in assembly-sized mode, but usually for us, we are running it with every individual channel resolved. But Cobra TF standalone doesn't have the information it needs to be able to model these things. So how do you understand the mixing after a grid spacer? How do you understand the redistributions and the pressure drops? And so it uses star CCM plus CFD code to be able to run a whole lot of CFD calculations to define the models that are built inside of Cobra. There is a surface chemistry capability that I'll talk about in a little bit called Mamba, that models that crud growth. And the Bison fuel performance code, it doesn't have some external thing feeding it because it actually can run in 1D, 2D, or 3D. And so it can be a low fidelity capability that we use, or it can be its own higher fidelity capability, whether it's using its low fidelity or the high fidelity, it uses the same fundamental materials and models and that kind of thing. So all of these codes, each of these codes uses different toolkits. So Petsy is a math solver out of Argonne National Lab in Chicago. Trilinos is a math solver out of Sandia National Lab in Albuquerque. Moose is a math solver out of Idaho National Lab, and Dakota is uncertainty quantification toolset out of Sandia. In the beginning, there were people that were like, I am a Trilinos person, we must use Trilinos. Some people went, no, I'm a Petsy person, we must use Petsy. We went, this is ridiculous, it's just math solving. Use whichever one you want, but we have to have the ability to support them using whichever one they want. And then there are some things that enable solution transfer between meshes. So if I have a mesh on my neutronics that looks like this, and then there's a subchannel mesh that looked like this, how do I transfer the temperatures and the densities here to this region here for this pin cell? Because that region is the exact same as 1/4 of this. And so there are tool sets that are there that are designed to let you transfer that data from this collection of mesh cells to this one big mesh cell and then back and forth. Whenever you're using a code, you need to understand the impact of how big is that mesh. And so if we had this size mesh with 1 centimeter tall, if you're using a code, you should spend the time to say, well, what if I made that a 1/2 centimeter or a 1/4 centimeter? Is my answer changing? Because if my answer is still changing, then I probably shouldn't just wait on 1 centimeter. And so you also, when you're using this, you need the ability to start changing what this mesh is and changing what this mesh is. And so if you kind of hardwire that into your code, then it gets very difficult to change it. If I'm working on my neutronics code and I want to change the way I do things, these tool sets let you more easily, here's what I'm giving them, and then they say, okay, I need to receive something. The focus on the end user. In general, when you have a bunch of individual codes, they individually write their own output. But that's not necessarily helpful for the end user because the end user wants one output from the one simulation. If they have to go look at 18 different output files for their information, it's going to make it difficult to do the analysis. And so we said, all right, we need to define a common input structure so that they can define one input for all of these codes. And we need to have them all write their output or collect their output to write it to one single output file that we can then pick it up and view it and visualize. Even just looking at the solution. Nobody looked on a regular basis at reactor data that was at this resolution, at the individual pin cell level. And so there really wasn't even a tool set to go, well, how do I look at these things? And so we had to develop the capability just to look at and evaluate and understand what the output was. And then whenever you're doing accident analysis, the LOCAs and the RIA, the reactivity insertion accident, you have to couple it with another code that goes beyond just the core. It has to look at the system. All of this was really focused on looking at the actual core itself. So some big challenges that aren't even, quite frankly, interesting science that all of us love. You have to figure out if each code is independently strong. You still have to figure out how you do the parallel work. Who's getting how many processors and where are those processors doing the work? You have to look at the global overall solution. When we drew on the board, solve neutronics, solve thermal hydraulics. If one code is doing one and another code is doing another, somebody has to be in charge of saying, we've converged, our solution is done. Understanding conservation. So if sometimes people will say, let me pass temperature. I computed temperature in my fuel code, let me pass temperature. Well, temperature isn't a conserved quantity. If I am a little bit off in my temperature, would you even know it? But if I passed power, and if I said I'm generating a megawatt of power, and you say I got power from you, and you sum it up and it's 2 megawatts of power, then suddenly there's going to be really big differences. And so understanding that conservation of properties, what properties should we be communicating? Do they need to be conserved? If they do, are they? And if they don't need to be conserved, how do we make sure we got the right solution past the right place? Each of the math solvers. So code compiling is a really, really big headache. But when in each of these codes, when it comes back there. So to use PETSI, they're going to say, I need to compile it. And I can compile it with Intel or GNU or whichever compiler. There's some particular versions of compilers that I'm going to work with and I'm not going to work with others. Another one may say, oh no, I don't like that one. I need to work with a different one. And so you have to work with these teams and these teams to make sure that are we all going to be able to work with GCC 9.1 or not? And so consistency amongst all of these compilers and math solvers, the processing, visualization of results. And one of the other things is understanding how can we replace codes if something's not working, if something comes along that's better. This was not the original one. Neither of these codes existed when this project started. This code was kind of frozen. It was a code developed by a guy who at Penn State who had passed away, and nobody was really using it very much. So it was kind of revived, but there were several codes that were picked up and attempted before that. And so how can we have an infrastructure where we say, well, this is the code we want now, but if there's a better code that comes along right later, how do we, take this one out and put that new one in? So having the ability to let this grow and change with time. And then overall, all of these codes were actually in the middle of development. And so it's not like it was a static code that we said, let me get the 2009 version of this code and let me use it. The codes were changing literally every day. And so if somebody changes impact and they could change it in a way that would mess up the coupling with the thermal fluids. They could change it in a way that changes the answers on some of our benchmark calculations. And so we need to have the ability to say, what is important to us? How do we know that these things are working? And create an entire suite of test problems that whenever somebody says, I changed my code, we can say, okay, you changed your code. Did you break something? And evaluate the quality of that change to make sure that nothing was broken during the process. That stuff isn't science, but if you're not doing that thing, that kind of thing, you can't have a team working on a big project like this. So these are some snapshot results from that Vera core simulator. In this, we're only using a suite of the tool sets that are available. Both Impact and Cobra use the PETSI solvers, so Cholinos wasn't needed at all. They didn't need any of the mesh and solution transfer because Impact and Origin are, or Impact and Cobra are both Fortran 90 codes. Well, I guess Fortran 2003. They're both Fortran codes. And they said, we're working closely together. We're sitting in the same building. We can figure out how to do solution transfer. We don't need to use these tools. So in that, the CTF, Cobra TF, was modeling every single individual channel. It was modeling 2 fluids, so the vapor and the liquid, and 3 fields. So it said there's liquid, there's vapor, and then there is liquid film surrounding the rod. And we're going to model 14,000 coolant channels. This is only a quarter of a reactor. So if you're only modeling 1/4 of the reactor, you only have 14,000 individual channels. All of those channels can have cross flow between them. And all of the grid spacers are put together in full detail. So that thermal hydraulics capability was developed and tested, compared with a whole suite of benchmarks and experiments. The impact capability is that can resolve 3D radiation transport. Some features you sometimes see pop up in here is you see things like these little lines that are a little lighter. That's where the grid spacer is. And so you can actually see where does the power dip inside the grid spacer. In here, these little bubbles that are coming up, we plotted where is the subcooled nucleate boiling happening. And so down here, there isn't any boiling, and it's not until you get up to about 2/3 of the way up in the reactor when you start to have the little subcooled boiling happening on the surface of the rods. And so all of this full radiation transport was getting temperatures fed from Cobra, and Cobra was getting the powers, and so they were coupled and interacting and communicating at every single time step. And once there was a fully converged solution at that time step, we said, okay, now it's time to do time dependence. And Origin was modeling over 2 million individual spatial regions, 263 isotopes to do the isotopic depletion and decay. And so that's what was letting us get these multiple radial rings in every single fuel pin in the entire reactor. So each one of these is individually a really big calculation that requires a whole lot of computer memory. Even if you were like, I'm willing to wait the time, you can't store the amount of memory required for any one of these on one processor, on a one processor machine. They needed terabytes of memory. Yeah, terabytes of memory to store their data and their solutions. Any questions? Yeah.
How much time they have to compile?
How much time to write the code?
To compile, more like running.
Oh, to run the codes. So in this, at every single time step, it took about 30 minutes on a couple thousand processors. And so if you wanted to do a full 18-month depletion, then you might do 30 or 40 time steps. And so it would take, 16 hours or so. And so this is, you could say at the end of the day, I'm going to submit a job and then I'm going to go home and I'm going to let the computer work all night. And I come back in the morning. And in the morning, I see how did that depletion result come about? What did I learn from it? Do I need to change anything? So it would be difficult to do a reactor design if you say, let me try something today and tomorrow I'll try something else. It would take a very long time to get to a real design. But if you said, hey, I have a design and I want to understand, I think this is the power distribution. I want to have a higher resolution understanding of what that power is. Well, then you do all your work with the other code to do the design. And then you come to this one and say, okay, give me the details. That make sense?
Yeah.
All right. So this is also capable of doing accidents. And so this is a control rod injection and sort of a picture of some of the visualization capability that we had to add to it. So you could see this is the 1/4 of the reactor, and we identified the location where the power was the highest. And this is that assembly that had that highest power. And you can see that the control rod popped out. I believe it was this one popped out. And so you can see how there is high power around it, but there are a whole lot of rods around there that are also getting to a high power. This is the, as a function of, so this is varying as the accident happens. This is how that progression is happening. So where the axial power, let's see, yeah, that's the axial power distribution. And so you can see when that control rod moves out, it's where that control rod had been, where it gets that big spike in power. And so on this, you're able to look at and start to, as an engineer, go, wait a minute, what do I see? What am I concerned about? how can I dig in with more detail looking at each one of these rods? So to do the actual algorithm for overall driving this, you first do a coupled solve at time equals 0. And so you first say, okay, let's start at hot 0 power. The reactor is completely hot, but it's producing no power. So it's uniform temperatures everywhere. And you do the full coupled impact plus CTF calculation. And you get to, here is my full power distribution. And then once you know your fluxes, once you know your cross sections, then you can do your depletion. And so a predictor corrector approach is doing this. And so what you're doing is you're saying, I'm going to first take a guess at what my flux is. So I get my flux. So I do a coupled solve to get my flux and my cross sections. And then I do my isotopic depletion. So if you remember the depletion equations, dN dt equals my loss. So for each isotope, my loss from that isotope. And so radioactive decay plus any cross sections that would make it remove times the flux for that isotope, plus any additions. So summing all the other isotopes, 1 to 263 of any radioactive decay from, we'll call this J, from J to I, plus any reactions, sigma J to I, and J. And so the depletion equations are going to march things in time. So this was a static at this moment, and then the depletion will march things in time. And so we first say, let me guess phi and sigma at time 0. And let me deplete. And so this is assuming that that flux was constant. And so this is solving these depletion equations with time 0 for each of these values. Your lambdas don't change, they're decay constants. And so you got from your neutronics an initial estimate for what phi and sigmas were, and you depleted to get some new isotopes. And at time equals 1. Then you say, now let me do another coupled solve at n equals 1. So here I do my coupled solve with n at time equals 1 to get a new phi and sigma at time 1. And then I can say, okay, now let me resolve the time step. So this is the predict, and this is the correct. So I resolve my time step with these values at 1 to get another update for what n is. And A, n at time equal 1, B. Then I say my true n at time equal 1 is 1/2 of NA plus NB. And so I start with a flux from the early time to get a value. And then I get a flux from the end value to get a new value. And I say my predicted plus corrected one is the average of both of those. Does that make sense? All right. So in that process, for every one of these time steps, I'm going to do a predict, a coupled solve, a correct, and then a coupled solve to get my final total coupled solve isotopes. And then I output my results in that time step, and I continue to loop in time. And so this is the process for a steady state type of calculation. If we had a time-dependent calculation, I'll get into that in a little bit later today of how that changes. But even in a time-dependent, you wind up with the same, we do a lot of these coupled solves. And so we can turn our focus to Anything that we do to advance the time process would reduce the number of coupled solves we have. But if we improve how fast we're doing the coupled solve, it's going to help no matter what. Any questions? All right, so the first and easiest one that I mentioned before was we have this Picard iteration where you solve one, solve the next. So you iterate to convergence with M being my iteration step. And so I solve CTF, I get my given some power at the previous time, so that's power at iteration M minus 1 to get my new temperature and density at iteration M. And then I solve impact. I do my 2-dimensional transport to get my cross sections, and then I do my full 3-dimensional transport to get my eigenvalue and my flux and my powers. And then I mentioned yesterday, we put in some weighting factor to dampen how much change there is. And so we said we're just going to dampen the power. So a little bit of PM minus 1 and some of this new power to lead to our new final PM. And we just iterate through this process until it's converged. In parallel computing space, CTF had 200 assemblies and flow was going vertical. And it wound up getting to the point where they said, you know, if I have more than 200 processors, I actually start slowing down because I'm spending all my commute time telling the other processors what's happening. And so CTF said, I don't want more than 200 processors. But Impact said, I can't solve this problem with only 200 processors. I need more memory than that. So Impact needed 1,000 processors and CTF needed 200. And we said, let's let Impact drive that power to temperature. So it sends the power to Cobra, and then it says, let me get the temperature and density from Cobra, and it's going to manage the convergence. It's going to manage this process and decide when am I converged. And so if we look at what processors are happening, we have a period of time where Cobra is working by itself, and we have a period of time where Impact is working by itself. And so they can use the same processors. They don't have to be on different sets of processors. So 800 processors sit idle for a period of time and do nothing, while Cobra is using its 200 to get the answer. And then 1,000 processors all start working together to get the Impact solution. And so we've split this up in the parallel domain, and we have our fraction of wall time says, well, CTF is down here with this fraction, and Impact is at that bigger fraction. And so if we have more processors, we can shrink Impact down some, but we still wind up with this big empty space that CTF can't even use all of those processors. Any questions on that? All right. Online, please jump in. And so in doing that, with that, what is that weighting, what is that damping factor? That alpha term that I mentioned yesterday, the omega term listed here in this picture. There is a range for how many iterations does it take to converge. And so if you put in a weighting factor of 0.5, then whether the power was at 80 or 100 or 120%, it still took in the range of 15 or so iterations to converge. So you would go through this process, that to that, that to that, that to that, 15 times, and it would converge. But as you increase your power, the optimal weighting factor changed. So at a low power, that optimal weighting factor was around 0.6. As it got up to a higher power, it went down to 0.5. And you can easily surmise that you would probably, at even lower powers, have a better damping factor that was way down up here at 0.9. But if you tried to use a weighting factor of 0.8 or 0.9 with 120% power, it would not converge. So there is a window where it is possible for it to converge, and a big range where there is no way it's going to converge at all. And so you have to be very careful in how do I define what that damping factor is? Am I keeping an eye on it? Because when you're operating your reactor, sometimes you operate at 100% power, and sometimes you drop down to 20% power. And so if you pick one damping factor and you say, I'm going to stick with that, and your problem changes on power, you might get yourself into a range where suddenly this method is not going to converge at all. Any questions? So that's a challenge. So we needed to start looking into some other things. It would work. It could get a lot of progress done, especially on these reactors where we're just going up to full power and staying. So we started looking at some collaborations with some real mathematicians. I am a very mathematically inclined nuclear engineer, but when I start interacting with true mathematicians, I realize I'm not a mathematician. Anderson acceleration is a method that was invented decades ago, but has hardly been used. The idea in Anderson acceleration is if you have multiple instances of a solution, then you can take a look at with multiple of those instances and what the approximate error was in each of those solutions. So if you have some way of guessing an approximate error and you have multiple solutions from multiple iterations, how can I put those solutions together to minimize what should be the error? And so you do the exact same process. You solve CTF, you solve impact, and then you say, okay, now let me hand this to a math tool and say, what should based on the information I have, what is the power and temperatures that would minimize that error? But because CTF is working on the old one, and now impact is also working on the old temperature and the old density, they don't have to solve CTF and then impact. Here, impact used the very latest temperatures and densities that just came from CTF. Here we said, we're going to allow impact and CTF to use the old information. And so now they can run at the same time. Now I can have all 12, now, and I go from 1,000 to 1,200 cores, I can reduce the total amount of runtime for every iteration because it's really only how long did impact take. And so I dropped the runtime significantly for every iteration, but I needed 200 more processors in order to do it. And in doing so, I let an advanced math solver take a look at this problem and say, how do I reduce the number? How do I reduce this problem so I get what should be based on the information I have an optimal temperature, density, and power? And so when we did that, any questions on that process? All right. So when we did that, so Anderson acceleration has a term that is kind of like that weight function. It has what they call a mixing parameter. And it's how much do I weight the most recent answers as compared to the oldest answers. And so if you keep 5 answers, then the newer answers probably are more important than the older answers. So I should weight the newer ones more than those that were 5 ago. And so that mixing parameter is kind of the same way as the damping factor. The user gets to say, let me pick a mixing parameter. And when we look at that at each of these different powers, independent of what that mixing fraction was, it was consistently converging. Every single time, it was always converging. It was converging with less total number of iterations, pretty much always. And so there was no concern about now have I gotten into a state where I can no longer converge because the power changed. And so far more robust. And in doing so, it was able to say, let's leverage some of these advanced math solvers, even those created decades ago. A lot of times things in the math community don't work their way to an engineering community for a long time, because it's hard for the engineers to see where is it needed and where it can be used. And so instead of having these overlapping domains, Anderson acceleration allowed you to have the separate impact and Cobra domains. So when we look at it, the time for every single time we solve Cobra, 200 processors working on all of these unknowns, it takes 3 minutes to do one steady state calculation. Impact took 20 minutes to do, on its 1,000 processors, took 21 minutes to do a single calculation. The 2-dimensional transport was about 60% of a minute, and the 3D diffusion part was 1.5 minutes. And so in this process, this is sort of the breakdown for how much time was spent in each of these chunks. Overall, when we looked at it, the Anderson acceleration only wound up taking about 6 iterations. The Picard iteration with the optimal weighting fraction was 11 iterations. Because they were doing mostly the same amount of work per iteration, this was about half the amount of runtime as the Picard iteration. And so we felt like we had a really big win there. We had something that was robust and stable, converged in 6 iterations. And each one of those iterations, we were doing 6 fully solved impact and 6 fully solved CTF. But only 6 iterations seemed pretty good. We were pretty happy with that. But then we looked at, well, what if we would do that block elimination, the one that I talked about before? We said, you know, the impact time was still 21 minutes. So we had 1,000 processors working as hard as they could for 21 minutes. And then we'd have 3 minutes where 800 processors were just sitting around doing nothing, and those 200 processors were working. When we switched to Anderson, it was okay. Well, we had 200 processors that were sitting around doing nothing for 18 minutes because they only needed 3 minutes of work per time. But we looked at this and we said, you know, if we could just do 1 transport and 1 diffusion and 1 Cobra TF, now if we only need 6 Cobra TFs to get the right answer, that could be a whole lot faster. But is that going to be enough to get that full impact? And so you can see on here that if you combine the 2D and the 3D, this is about 2.1 minutes per transport to diffusion is 2.1 minutes. So each time you were solving impact, it took about 10 impact iterations. So if there were 6 global nonlinear iterations, that means there were 60 impact iterations in all. That makes sense? So we said, what if we can embed this inside of the impact iteration loop? And so now I say I'm going to solve CTF, and then I'm just do 1 impact iteration. Before, when I was fully solving impact, it took 10 times we had to go through this. Now, and then the global iteration took 6. So we did 60 of these impact iterations. So if the total number of this problem takes less than 60 iterations, we might be saving time overall, even though we may do a whole lot more CTF solves, but the CTF didn't take as long. And so when we did that, when we did the elimination approach, we were back up to 11 iterations. But our wall time dropped dramatically because instead of 60 impact iterations, there were only 11 total impact iterations that were needed. Instead of 6 CTF solves, you had to go up to 11, but the CTF solve took a lot less time. And so we were able to drop that wall time down to the 30 minutes, which is where we are right now. The 30 minutes is great, but it still actually has a similar damping issue, but it's not as bad. And so it turns out, that we can look and we can theoretically understand what's happening here and understand why it's happening. And we know we have a very small window of where an acceptable damping factor is. But when we put this in the elimination approach, then we are kind of intertwining these solves where every single impact iteration we're completely solving for the temperature. So we're eliminating sort of that temperature from the iteration. And now what we found is we have a much more stable, and we haven't produced a plot of this, but it is a much more stable range of acceptable. And so it's not nearly as strong as this, and certainly not down in the 6 range. So, but it's in the 30 down and then back up to 30 again. So on one hand, you look at it and you go, it's still not as, it's far less predictable. And so we can see in our calculations when we're doing a depletion, if we're changing the power up and down, most of our iterations will take 30 minutes, 30 minutes for a coupled solve, 30 minutes for a coupled solve. But then every once in a while it'll go, oh, that one took an hour and a half for a coupled solve. If we were using Anderson right now, we would be in 2 hours per coupled solve. Where did it go? I was going the wrong way. We would be in 126 minutes. We'd be in 2 hours per coupled solve, but we would know it's always going to be 2 hours. There won't be some variability of is it 30 minutes or is it 2 hours, or maybe it could be 6 hours, or maybe it doesn't converge at all. And so this elimination approach has more likelihood that fundamentally it's just not going to converge, and the user has to go, wait, I left for the night, I started it, I came back in the morning and expected a result, and I didn't get my result. But if we switch to Anderson, it's 4 times as long. So then they go, I know I'm going to get a result, but it's going to be 4 days from now. It's not going to be tomorrow. So our users have said, I'm willing to learn how to play with that value, and I can start trying to get real results in a much faster time frame. So I'm willing to take the risk of that sensitivity for a factor of 4 speed up in runtime. So, questions? All right, so now, but fundamentally, we don't actually understand why that Gauss elimination is more stable. We don't even understand theoretically why it converges. Theoretically, there is no reason to believe that should converge. If you sit down and you do a mathematical assessment of, will this converge? It's a, I don't really know. And so I'd love to work with some mathematicians at some point and go, let's sit down and try to understand this approach. And mathematically, how can we create a little mini problem that we can understand what's happening and why it converges, because that might give us more insight into creating a damping factor that is more robust. So there is another one that I'll talk about later in the week. That is Jacobian-free Newton-free law, JFNK, preconditioned Jacobian-free Newton-free law. With this, it is effectively called a more intrusive method. You can't just say, hey, code, you solve, and then you solve. You need the code to say, I'm going to give you an answer and you tell me how bad it is. And that's all I need to do is you give me the answer and tell me how bad it is. But I also need a way to look at a global problem and make an approximate guess for the answer. The preconditioning is, how do I accelerate the problem and make an approximate guess? And the just give me the error that you have right now is what is needed for JFNK. In general, some codes weren't designed to do that at all. You can't give Cobra TF here's a power and some steady state temperatures, tell me how bad they are. CTF will say, the only way I can tell you how bad they are is if I took the powers and I solved the problem and I got the new temperatures and then I compared them and gave you the answer. And they're like, no, that process shouldn't be very hard. It should be easy to tell me how bad the answer is by giving me the residual. So we developed 2 sort of modified versions. One of the nice things about JFNK is once it gets close to the answer, it solves the answer. So if we wanted the answer to convergence tolerance of 10 to the negative 4 or 5 or 6 or 7, once it got close, it was like, boom, I nailed the answer. Picard, as you try to get more and more error reduced out of your solution, the runtime takes longer and longer. The same thing for Anderson. Each time you try to increase how accurate you have that answer, you increase how long it took. And so we created some modified versions of Jacobian-free Newton-free law to try to overcome this CTF thing. And we got some good progress. And so we went, we could see how possibly this might be able to save us a factor of 2, but it's going to take a whole lot of work. And so if you're going to do this, it's better to write your code in a way that was designed from the get-go to work with that kind of a math solver. So we discarded it for now, but you'll see it come up later this week. So algorithms, multiphysics couple. What questions do y'all have? Online, you guys got anything? All right. So we'll start looking at some challenge problems. So now if we want to incorporate some chemistry, so this crud, we're talking about what the crud is. Boron in a PWR is added to coolant to control reactivity. Those metal ions, lithium, iron, and nickel from the piping get released into the coolant. All of the complex flow that comes out of grid spacers and mixing vanes leads to complex temperatures on the surface of the cladding. And where there is subcooled nucleate boiling happening, you have this crud growth, and nickel ferrite, nickel, iron, oxygen crud grows on that surface of the cladding. It's very porous. And so you can have a lithium oxygen boron that will precipitate inside of that crud. And that boron captures neutrons. And so if we look at where is that subcooled boiling happening, it's generally happening in the upper sort of third of the reactor. And so if boron starts getting caught in that upper third of the reactor and staying there, even though the rest of the reactor has it flowing through the water, then you wind up having more neutron absorption here, and it drops the power lower there. And so you assumed you had some cosine power shape axially, and now you have a big power at the bottom and lower at the top. And that matters because in a PWR, the control rods come in from the top. And so when you say, I ran a safety calculation and I had a reactivity insertion accident, I put in control rods to shut it down. Well, your control rods are supposed to start absorbing a ton of neutrons once they get maybe 6, 8 inches into the core. But if the crud has dropped the power down at the top, the control rod has to get maybe 2 feet into the core before it really starts absorbing neutrons. And because of that, that means it's going to take longer to shut the reactor down. And so the reactor utilities have to be very aware of what is the power distribution. And if the power distribution at the top gets too low, then they actually have to reduce power and they can't produce as much electricity as they want. And so that is this crud-induced power shift. Is by dropping the power up there, it shifts the power to the bottom, and they have to reduce that power operation. And so if they are reducing the power from 100% to 70% to account for this, they're losing $300,000 a day. So the utilities really, really don't like crud-induced power shift, but they really have a difficult time with their tools understanding where this crud builds up. So if this is 5 in a 5 sort of mini assembly with 5 by 5 and the center pin being gone. So they ran an experiment, a flow experiment, and they said, let's put some grid spacers in here. Let's electrically heat these rods. Let's flow water through this little 5 by 5 assembly. And let's look at what the temperature looks like on it. And so this is sort of the unwrapped fuel rod. So you can see what that temperature variation is on it. And so if this is the temperature variation, the crud is preferentially going to grow at where these hot spots are, because those hot spots are where the subcooled nucleate boiling is going to happen. And so azimuthally around the outer surface of the rod, you have some regions that are hot, cold, and some regions that are hot. And so you're going to have different crud growth differently around this. And it all depends on the complexity of these grid spacers and mixing vanes and how they change the flow. But it's also a global thing, because you can't just look at one pin and say, what's the power and what's the flow temperature around that one pin, because that pin's power depends on everything else around. So we needed the full picture for all of the power in the full reactor with the resolution of every single individual pin, and even azimuthally. So if we have our pin sitting here with our Cobra sub-channel code, we can get, here is my temperature on this side, my temperature on this side, and this side. So I can break this up into 4 faces with 4 different temperatures with that same axial 1 centimeter resolution. But when we look here, we can see that variation is actually a whole lot more variation than just 4 regions. 4 isn't really enough to pick up all of that resolution that you get from a CFD calculation. So what we needed to do is we needed to say, let's use CFD, and let's use CFD to model flow through a grid spacer and downstream from a grid spacer to understand how it causes that flow to mix. And then we take the CFD and we take our subchannel and we say, how would we map on a finer mesh what that temperature should look like on the surface of that rod. And so then we can do, and here in this picture, it's showing 8 regions azimuthally. I think our default was 12 regions azimuthally. And instead of this being 1 centimeter, there were about 8 or 10 mesh axially for each one of those 1 centimeter cells. And on each one of these little faces, we needed to do a crud growth model. And so in it, we needed to say, okay, what's the temperature of the outer surface of the cladding? What is the temperature of the water? And how much of these metal ions are in the water? And with that knowledge of those temperatures and those metal ions, we can slowly model with time how that crud grows and thickens and expands on that face. And every one of these faces is done individually. And so on a single rod, we can create a map of how much crud is grown on that distribution. And in that crud, there is boron. So what is the distribution of boron on that one rod? And so this is a picture of the axial distribution of how thick the crud grows. And this is a picture of the boron inside of the crud azimuthally around the rod and from the bottom to the top. And so before, in the tools that we talked about yesterday, they would say, you know, give me some idea of what the temperature is for that average rod. And I'll use that average rod as representative of all of these rods. And when they compared it with experiments, it was always under predicting. And so they'd always say, okay, I'm going to have to take the average rod and just increase its temperature by 20%, just so that I can be conservative. And then I tell everybody, you know, this is how you design a reactor so that you won't, a fuel loading scheme, so that you don't have axial crud growth and axial power shift because of the crud growth. And it was leading the utilities to buy lots of extra fuel assemblies. As we were able to give them this information, they were able to have a whole lot more detail and say, okay, now I understand what is happening. I understand where and why and how this crud is growing. And maybe I can buy a whole lot less new fuel assemblies and save money on fuel purchases and not have to be operating in such a careful environment because I have more knowledge of what's happening. That makes sense? So, how do we actually solve that problem? So now we have to add some chemistry. And so when we looked at that, the chemistry code was also a Fortran code. And it actually is a really simple one-dimensional chemistry code. One-dimensional corrosion crud growth code. There's lots of physics that went into it, and a lot of physics feeding in, you know, this is the data you use for it. But effectively, you had this one-dimensional code, but there were millions of those calculations happening all the time because you had lots and lots of faces on these fuel rods. But because it was Fortran and because Cobra was already doing time step to steady state, it wasn't solve for me the steady state temperatures and flow conditions. It was doing let me march in time to steady state. We could do the same thing with the crud, is we could just say, okay, every Cobra time step, let's let the crud grow a little bit also. And so we varied inside of that crud growth. It would provide that here is my crud growth during this time zone. Everything else could stay the same. I went from CTF alone to CTF plus Mamba, and so the runtime increased a little bit. But overall, the iteration, the structure followed the exact same path. Questions?
You have one.
Oh, no. Online, what's your question? Patricia, did you have a question?
Yes, doctor.
Yes.
I have one question. This overlapping domains process is the one that corresponds to the Picard procedure, right?
You mean the overlapping domains? So yes, so in the block elimination, we do the same approach as we do in Picard. We solve one and then we solve the other.
Okay. Thank you.
Yep. Any other questions? All right, so actually, I'm just going to highlight that. So, nope, I don't have the picture up here. So, up here, when we jump to integrating with X-core modeling, so if we looked at the Vera picture for the CRUD capability, it was exactly like just the normal core simulator capability, except it added the chemistry piece. Another thing that we did, since we had a Monte Carlo code that had the capability to communicate through data transfer using these data transfer tools here, we knew that we could fundamentally go, let's take a look at, could we solve for the full power distribution in the reactor core, and then understand what impact it's going to have as far as irradiation and activation of the pressure vessel. So here we have our core with all the fluid pins and assemblies, the core baffle and the core barrel, and then out here we have our pressure vessel. Most reactors will actually have a thermal shield in here that we added, but I don't have for this picture. And so in general, if we wanted to solve the neutron flux out here with impact, we could have done that, but it gets way beyond the reactor core. Distance-wise, it's going a long ways. And from a radiation transport standpoint, there you wind up having to have a lot of different directions that you're modeling. And you have to have different energy fidelity because the particles that are getting out here and impacting this, you often need to focus on different energies because it's a much higher focus on high energy reactions. So the continuous energy Monte Carlo codes have no approximations in space and energy and direction of travel. And so you have a real benefit of, if we know the fission distribution coming from our reactor core, in which impact can tell us at any moment in time what is the full fission distribution, we could feed that fission distribution, that source of neutrons, to a Monte Carlo code, and it could just do a fixed source Monte Carlo calculation. And it can do the radiation transport all the way out here to this vessel. And if we model this over the 1 18-month fuel cycle, we can see how much irradiation has been added to that. And all of that irradiation out there is starting to weaken that pressure vessel. It's very little, but over the course of 60 years, it can be significant. And so we have probably 20 different reactors that we have modeled their entire lifetime. And so we've been able to say, let's model the first cycle and the second, third, fourth, 21st, 23rd, to figure out how over the life of that pressure vessel, these fuel assemblies get changed out all the time. This pressure vessel is always there and getting irradiated. How much irradiation has gone there, so we can start to understand what impact is there for the on the materials. So to do this, we had a standard full coupled impact plus CTF calculation. And then we needed to pass that data to the Monte Carlo and let the impact continue doing what it was doing before. And so we're able to model the fluence on the pressure vessel. We're able to model X-core detectors. So if we wanted to know what would a detector outside see. And it's also generally, we said, okay, let's make this easy to use. So there could be one execution that says, hit play, and we get all of the power stuff as well as all of that external stuff. And so in that process, the way, well, so any question on what that is? Let's talk about how we did it in a minute. You guys get why, what we did and why we did it? So right now, as these reactors, so most of the US reactors were originally licensed for 40 years of operation. And we talked yesterday about the coupons that they have little samples of what this pressure vessel metal is. And they want to know how that material changes as it's getting irradiated. And so they keep those coupons sitting here on the outside, and every couple of years they take one and they test it. But the reactor was designed for 40 years. And so originally they said, well, we'll just take a coupon every couple of years. And then they said, oh, let's go from 40 years, let's get a 20-year extension. Let's go out to 60 years. And so most all of the reactors in the US are in the 40 to 60 year time frame. And some of them are saying, you know, let me go ahead and go to 80 years. Well, there were coupons designed for 40 years of operation, and you can't add more coupons. And so they're starting to say, let's take those coupons and sample them less. Let's maybe not go as often as we did originally, but extend it out to more and more years between it. And so we want to have a better understanding of the detailed distribution. And those samples might have been right here, but the highest irradiated piece might be right here. So to do that, what we did was time lagged Monte Carlo transport. And so we had in our domain, we had our original 1,000 processors, 200 for CTF plus Mamba, 1,000 for impact, and Shift just needed 50 extra processors. And so if we added 50 processors to Shift, then it could, in the time it takes to do the full coupled time solve for one impact Cobra TF coupled physics calculation, it could do all of its 50 with its 50 processors, it could do that fluence calculation. And so now our driving code would look like this. If we're on the impact domain of processors, 1,000, I'm going to do a coupled physics solve at hot zero power. And then I'm going to start looping in time. And so I'm going to go, I'm going to do my predictor and my coupled solve and my corrector and then my coupled solve. And then I'm going to take my final solution for that time step and I'm going to pass it over to Shift. And then I'm going to keep moving on, output my results, and then continue in that loop. The other set of processors just sat there and waited at first. And it waited for 30 minutes and 30 minutes and 30 minutes. And then after an hour and a half, it's finally got the first data that it could use. It said, all right, now I'm ready to start using my 50 processors and start working. So it was working on time step 1 while this was doing time step 2. And then once it got done with time step 2, it passed its data over and Shift said, oh, good, you finally finished. I'm ready to start again. And so Shift was always in a waiting to receive the data. Once I receive it, I'm going to start using my processors to go through that fixed source calculation. And so now for the cost of going from 1,000 to 1,050 cores, you get not only the full reactor physics calculation with the CRUD, with all that other detail, you also get the X-core irradiation of the pressure vessel information as well. What Shift is doing is Shift does a forward, adjoint, and then fixed source Monte Carlo calculation. So Shift has embedded inside of it a deterministic transport solver that will effectively guess for what the flux is everywhere so that it can efficiently start particles where it needs to on its continuous energy Monte Carlo calculation. Any questions?
Yes, doctor. I have another question.
Yes.
Is it faster to use Monte Carlo instead of using the deterministic method?
That question is something that should always be asked over and over and over. And the answer is absolutely yes and absolutely no.
Oh,
It completely depends on what information you want.
Oh.
So it turns out, if you want to do what we're doing here with impact, with a Monte Carlo calculation, you have to calculate what the power is on every one of those 3 million mesh cells that you're going to do depletion. And so you have to tally a whole lot of tallies. And Monte Carlo also doesn't like to do the embedded ATH feedback inside of the Monte Carlo calculation. Nobody's really done that. We don't understand why it converges with deterministic transport. Monte Carlo would add even more challenges. So I'll talk in more detail about Monte Carlo coupled physics calculations later. But in general, it's a yes, you can do it, and yes, there are times when it makes sense and you should. And but for this problem of interest, we tried it and went, no, absolutely not. Because shift could not hold all of the information needed to be able to pass the fluxes and the microscopic cross sections and the powers to the other physics domains, because it needed more memory. So you had to use domain decomposed Monte Carlo, and that doesn't exist yet.
Okay. Thank you.
Yep. So the next piece was, how do we handle fuel temperatures? So Bison was our fuel performance code. Bison was the code that we were using whenever we were going, okay, we want to know, inside of Cobra, there was a built-in fuel temperature capability. Let me do that 1D conduction. Kind of like Simulate 3K has built in a 1D conduction capability, but it could do it for every single pin cell at all of these axial heights. But the way it got its data was we'd run Bison and we'd say, okay, let's use Bison to generate some data that we use to calibrate where that CTF is. Similarly, as we talked about yesterday, there were a whole lot of experiments that have been run for fuel performance to calibrate these one-dimensional models to make them pretty reasonable. But there's a lot of multi-dimensional physics that come into play. And so it would be so much better if we could let Cobra TF do the subchannel flow and let Bison do all of the fuel performance. And so now we have a full true fuel performance code with all of the cladding creep down and fission gas release and all of that physics that is in fuel performance code without some tuned calibrated thing. And we have all of these things fully integrated and linking together. This expands because now we have to add Bison, and it uses libmesh to manage its mesh. And Bison is built on top of Moose to do a whole lot of its solver connection. And the way we were going to do data transfer between all of these things, like with Shift, we use DTK, which is built, which leverages Trilinos to do a whole lot of that communication. And so the idea is every single coupled physics solve, we get all of these fully converged and then we deplete in time. But fuel performance has time dependence too. So in the simplified CTF models, you just say, here is my power, here are these different parameterized things like total integrated power of the life of this fuel rod. And the model doesn't care about how it got to where it is. It wants to know what's my temperature, what's my burn up, what are my materials, and it just uses that. But structural mechanics doesn't behave like that. Structural mechanics, there is a fundamental dependence on how did I get to where I am now. cladding creep down is fundamentally dependent on I need to slowly creep in a plastic form. And so Bison is inherently a time-dependent code. It is not a steady state code. So with Bison, with CTF, we were marching to steady state. So it's a time-dependent code, but the way we were using it was get to steady state. And so it just takes time steps until the things aren't changing with time any longer. It knows it's steady state, it says it's done. With Bison, it is I had some initial state here, and you told me a power, and you told me a clad surface temperature, and you told me some period of time that it's operating, and I got to a new state. But if this is in a coupled scheme, then the overall driver could say, that's nice, thanks for that information. I used it, but now we need to go back and do that state again. And so it has to do this time step over and over for each one of these coupled physics solves. Does that make sense?
Yes.
All right. So one option is let's not have them coupled. So take a step back and go, you know what, maybe we don't need them coupled. Maybe instead, we just want the Bison solution. So maybe what we do is we just say, let's treat all of this the way we were doing it before, but we treat Bison the way we treated shift. After we have, at the end of this time step, what we know what the powers and the clad surface temperature from the coolant is, then we can pass that information over to Bison and it can compute all of the fuel. And so now we get the understanding of the fuel physics right away without having to do any standalone separate hand-us data to our fuels people and let them do the analysis. That fuels analysis comes with it, but we can still operate and interact in the exact same coupled physics approach we have. And so this is that same one-way coupling style, inline time lag approach. So similar to shift, we have Bison, 500 processors for 15,000 fuel rods. Our impact solves one time step. Vera passes over to Bison. The separate set of 500 processors takes and runs all of those 15,000 fuel rods to compute what the new fuel results are. And it just stores it and it keeps it. And that way, when the analyst at the end wants to know what happened with the fuel, they have the result and it came out of full fuel performance capability. But we assume that the built-in temperature inside of Cobra TF is just fine. So with that approach, we went from 1,000 to 1,500 processors, but now we got all of that extra information from the fuel performance. It didn't slow down. It's still a 16-hour calculation. It's just instead of 16 hours on 1,000, it's 16 hours on 1,500 processors. And if you have a big computer, why not? Any questions? But if we wanted to do fully coupled, now what we have to do on our block elimination, we're going to try to still do it in the same block elimination approach. So now, in the ideal world, we had 800 processors that were doing nothing with Bison. They were just sitting, or with CTF, they were just sitting idle whenever CTF was running. Well, ideally, we'd use 800 processors, and we would do all 15,000 of those fuel pins, and Bison would take the same amount of time as CTF or less. And if that were the case, then we could march through this entire process, and on 1,000 processors, we'd still get the exact same total runtime. We'd have to time lag in some, or iteration lag the power. So we give the power to Bison, and in general, if Bison is a full two-dimensional RZ fuel code, we don't know how much heat came out of that Bison rod until we solved Bison. But Bison has, I mentioned, multiple levels of fidelity. It can do 1D, 2D, 3D. So if we use the 1D version of Bison, then we know any heat we put into the center of the fuel rod is going to come out the cladding on the outside. And so Mamba and CTF don't have to wait for Bison to finish before it gets what its surface heat flux is. And so we can follow the same process, one impact iteration, solve the heat transfer. we have to lag what the cladding surface temperature is. So we use the cladding surface temperature from CTF and Mamba from the previous iteration. And so there's a little bit of error introduced here. But we can iterate this and it can march its way to convergence. And this process does work. The problem is it doesn't work on 800 processors. Because of the size of the problem, Bison needs 1,200 processors to be able to do in any kind of reasonable time the fuel pin, 15,000 fuel pin calculations. And so with this one-dimensional Bison, modeling every single one of them, with all of the fuel physics in it. So it is dramatically more than the temperature solved inside of CTF, but it's taking a lot more time, or taking a lot more time, and it needs a lot more processors. And so from the user standpoint, they said, wait a minute, you're gonna add double the runtime, and you're gonna double the number of processors I need. And that's what I'm getting for this fully coupled fuel performance. But if I did the inline, all I'd have to add, I'd still get the fuel result by doing this. It only had 1,500 processors and it was the same amount of runtime. And they said, well, does the answer change? Because if the CTF model came from Bison, this is going to be a pretty good model. And if I compare the fuel performance results with this approach versus the fully coupled fuel performance results, if there's no difference in the answer, why would I spend more processors and more time doing it? And so in that, the end users wound up saying, I like that time lag one. I don't like more time and more processors if the answer isn't changing at all. But this isn't really the end of the story. One of the things that came back as feedback is we went back to the people that developed Bison and we said, you got to get faster. Right now, you're a bottleneck. You got to get faster. You got to work on that, got to improve that speed. And so there's a team of people at Idaho National Lab that are looking at how do we speed up this and make this a whole lot faster. But we also could reevaluate Anderson acceleration because this was in that block elimination structure. If we did it from Anderson acceleration, then we might jump to 3,000 cores. But we might be able to do 3,000 cores in 6 iterations in this amount of time, which may not be that different from this amount of time. And so with that, Anderson acceleration might be a significantly better approach that we should consider and use if we wanted to do that fully coupled fuel performance and reactor physics. So I mentioned this aspect of the fuel. So we actually have, let's see what time. Oh, I'm running out of time. All right. Myself what I have afterwards. Okay, that is it. All right, good, perfect timing. So there are actually a variety of these fuel temperature things that can all kind of work independently. So one approach was before we had a solver for temperature inside of Cobra because it was a flow code. It didn't have a fuel model. We said we needed to add a fuel model. And so we just created a little interpolation function. And we said, let's run Bison a whole bunch. And just like we have cross sections interpolated for lattice physics to core diffusion, we said, let me just get if I tell you the power and the burn up, and here's my time, you tell me what my temperature should be. And so we created some simple Bison generated model. And in that, we have this same process where we iterate in convergence. We do our impact, we do our heat transfer, our fuel can solve and our Cobra can solve. It doesn't matter which one because they don't depend on each other. We know all the heat going into the fuel comes out into that channel. When we switched to CTF, computing its own fuel temperatures, we added this heat transfer that takes in the power, and now it's going to take in the power to the fuel, and it's going to conduct it out of the fuel and into the coolant and do the full time stepping to convergence. And so now CTF manages it entirely. But we added some more work to it, and so it slowed CTF down a little bit. But the overall iteration scheme didn't change at all by going from a interpolated table to an actual model. When we put in that 1D, which I'm calling 1.5D, that's the traditional name for it. Then we said, okay, now we have a, we're doing our heat transfer stuff in parallel. So we do our CTF. We know that all of the heat is going out radially. So I don't have to worry about the heat flux, because the heat flux, anything going into fuel in that axial region comes out the fuel. And so I can do my steady state coolant flow independent of the fuel. And my fuel, it needs a clad surface temperature. And so I use the clad surface temperature from that previous iteration. And so I lag in time that clad surface temperature. When it goes to actual fully coupled, so we also ran this with the full 2D RZ Bison. The 1200 processors and a more time, this got to, oh,
Yes, one with
yeah,
Israel.
Israel, did you have a question? All right, jump in anytime. So when we did that, then we had to say, now I have to solve with the 2D, now I have to solve Bison with some guess for what that clad surface temperature is. But I also have to solve Cobra TF with some guess for what the surface heat flux is. Because now some of the heat, when you run a two-dimensional Bison, some of the power deposited here might conduct axially and then radially out. And so what was deposited in one axial node might come out in a different axial node. And so I have to lag by iteration that surface heat flux. So that's all I have. Back to some of the original overarching points. Can this be used for design? Yes. Would you be very effective and efficient? Not right now. Now, if you had a whole bunch of machines that had a whole bunch of 1,000 processors, then you could fire off, let me do lots of design perturbations. And if you had a machine that had, was capable of doing 1,000 processor calculations at once, then you could just say, hey, let me give you 1,000 of these, let me come back the next day and let me analyze all 1,000 of these. And now that might be way more efficient than your one processor 5-minute check, check, check. So maybe if you had full supercomputing and you had access to your own full supercomputer, you could make that work and make that efficient. But far more useful for this was, hey, there were problems and things that this was made for, and they were aiming to solve these particular problems. And so it was geared and designed for that. It wasn't designed for normal operation. But there have been, there have been several reactors that have started up in several areas where it closely engaged with the nuclear industry sort of directly. The first one was in China, the first AP1000, Westinghouse's new advanced Gen 3+ light water reactor. They were going to be starting up that first one in about 2014, 2013. Oh no, yeah, 2015. So in 2015, they started that up. And around the same time, they started another traditional reactor, Watts Bar Unit 2, in Tennessee. And so Westinghouse was able to take the codes and say, we're going to use this and predict what will happen with startup when they do all of their startup testing, when they ramp up in power and come back down, because they do a whole lot of startup testing when they create a brand new reactor. And there is no validation for any of that reactor at all. And so they used these tools to try to predict what was going to happen before it started up. And the predictions were an order of magnitude more accurate than using the traditional tools. In the Watts Bar one, that was a TVA reactor and a Westinghouse design. So two of our partners working together, and they were like, this is perfect. This is very similar to these traditional reactors we don't expect very much to happen, but we have a couple of different little changes in here that aren't normal. And so they expected the predictions from the traditional tools predict exactly what would happen, and their answers on the traditional tools would be great, and our answers would be great, everybody would be happy. And when they started doing the zero power physics testing, they were off significantly. So there started to be concern about TVA was saying, did you give us the wrong fuel? Maybe you guys were supposed to give us some fuel and you gave us some bad fuel. It wasn't designed as it was supposed to be. Or maybe, you know, what's wrong with the fuel you gave us? And Westinghouse was saying, you know, you might have put the fuel in the wrong place. Maybe you put assembly A here and it should have been over there. This is probably your fault. And so they started having lawyers like, we're going at this because somebody messed up. The research team at Westinghouse and the research team at TVA were both able to pick up the Castle tools and say, okay, let's see if we understand the difference. And the Castle tools were significantly better than the traditional tools because of the small different changes that they had in it. And they were able to say, you planned and you told the regulator it was going to be this, and you're off by this much. But as you go up in power, they're going to get closer and closer. And so your answers are bad here at zero power, but they're going to get better with time. Because they were worried if it's bad at zero power, it could be even worse as you go up to full power. So we were able to show with these tools, they were able to pick up these tools and use them and show things will get better, relax, calm down, send your lawyers home. And everything calmed down and they were able to operate. And then we were able to, with Watts Bar, we were able to follow every single, so we were doing every hour time steps for the first 6 months of operation.
Did you find why the difference at the zero power?
Yes. So they, in the lattice physics calculation, you're assuming that it's in an infancy of that same type. And it was a different, if they had used color sets instead of just single assembly calculations, they wouldn't have had that error. And so once the research team at Westinghouse were able to tell the operations team at Westinghouse what was going on, the operations team at Westinghouse said, okay, let's go back and use color sets. And they were able to eliminate that error.
Because no leakage.
Yes. Yep, it was a leakage issue. And so from those standpoints, it has really been picked up and been useful on complete blind startup testing. The Duke Energy, which has about 8 reactors, has been using this for crud analysis to understand how can they choose more crud risky, what is traditionally called crud risky fuel loading patterns so that they buy less fuel. And it has been successful from the utility standpoint because they're buying less fuel, and Westinghouse is going, but you were buying our fuel. What just happened? So yeah, these things are starting to make an impact in the industry. Every has been using the fuel performance piece, trying to understand during load follow operations, as you go up and down in power, what is the impact, what is the increased risk of fuel failures. So that's what we did and how we did it. Any questions online?
Yes, doctor, another question. Even through a parallelization process, these codes are not that efficient?
What do you mean by the codes aren't that efficient?
Yes, you said that you can use a parallelization process to make faster calculations, but even through this process, these calculations are not enough faster yet.
Well, so part of it is, everybody is comfortable with what they're used to. And so if you've always driven a automatic transmission car and someone gives you the opportunity to drive a Ferrari, but you have to use a stick shift, you may think it's uncomfortable, even though it's way better car. So part of it is getting people broken out of the mold of, well, I need to have the answer in 5 minutes. I need one answer in 5 minutes, and I could do, I could do 12 answers in an hour. Getting them to change their mindset on how they do things to, well, maybe what I need to do is 100 answers overnight. But it's okay also that this isn't used for everything. Every tool has a purpose, and use the right tool for the purpose. The purpose of this tool is really in-depth understanding of something that you didn't understand before. You can use this tool for normal design operation, but it probably is not the best tool for that. And so always have multiple tools in your toolkit and use the right one for the job.
Okay. Thanks.
Mm-hmm.
There is another question. Yeah, come on. Francisco? You have your microphone closed. Thanks. Okay. We cannot hear your question. Okay.
All right. If there are no more questions, then that's all for today. We'll see you tomorrow.